In the previous lecture, we have started to deal with a very important concept of reciprocal lattice in solid state physics. And in that lecture, you have seen actually the basic definition of reciprocal lattice, how we can define the reciprocal lattice vectors. All those things we have discussed in the first lecture on this reciprocal lattice. Now in this second lecture on the same subject, we will see the important vector algebraic properties of reciprocal lattice. And these properties are very important in dealing with the study of crystal structure, and we will use it at several places when you study the problems related to the reciprocal lattice. So let us start to deal with the different properties of reciprocal lattice. The first property I have mentioned here is the reciprocal of the reciprocal lattice is the direct lattice. This is a very important property, and this is just equivalent to saying that if you can say that 1 over 5 is the reciprocal of the number 5. Okay? So, and when you will take again the reciprocal of 1 over 5, okay, 1 over 5, then you will get 5. So it means reciprocal of a number is the original number. Like that, you can say that when we will take the reciprocal lattice of a reciprocal lattice, then we will get the direct lattice. It means reciprocal of the reciprocal lattice is simply the direct lattice. Now we will prove or we will explain this very important property. And for this it is obvious that we have to actually find the primitive translation vector of the reciprocal of the reciprocal lattice primitive translation vectors. You know, we have seen that if you consider that A, B and C are the primitive translation vectors of a direct lattice, then we have denoted by the symbol A star, B star and C star the primitive translation vector of the reciprocal lattice. Now we will see when we will take actually the reciprocal of this A star, B star and C star, what we will get. You will see that actually the A star star will be equal to A. Similarly, the B star star will be equal to B and C star star will be equal to C. Okay, but how? We can see it very easily. So in order to prove this statement or this property which I have mentioned, we have to find the lattice vector A star star. It means you are going to define the reciprocal lattice vector of a reciprocal lattice vector. Okay. Now as we have seen that when we find the primitive translation vector of a reciprocal lattice of a direct lattice and you define A star, how you define it? You have seen in the first lecture that it is defined as B cross C over A dot B cross C. Okay, actually this scalar in the denominator, that is A dot B cross C, represents the volume of the direct lattice unit cell. Okay, and ABC are the primitive translation vector of the direct lattice. Here at the place of direct lattice we will use the reciprocal lattice and then we will find its reciprocal. So according to this definition, A star will be equal to what? That will be B star cross C star over A star dot B star cross C star. This is in accordance with this basic definition. You can also use the factor 2 pi as I have mentioned in the first lecture. But I have not used here 2 pi. You can use or you cannot use. Okay. Now, in the first lecture, we have discussed some of the important properties of this reciprocal lattice, and you have seen that this scalar product A dot A star is equal to 1. You have seen in the earlier lecture. So, if we will multiply the RHS of this equation 1 by this number, that is A dot A star, the result will remain unaffected, because after multiplying by 1, the result does not change. And so, this equation 1 can be written as A star star will be equal to B star cross C star divided by A star dot B star cross C star multiplied by this number A dot A star, which is simply equal to 1. Okay. And now, according to the definition of a scalar product, this RHS now can be written in this fashion. You can see this A star star can be written as A times what? A times A star dot B star cross C star over A star dot B star cross C star. Now you can see these two scalars will cancel out, and the remaining vector is only A. So what we are getting here? You can see when you take the reciprocal of reciprocal lattice, then you get the primitive translation vector of the direct lattice. So we have shown that A star star is equal to A. Okay. Actually, in the similar manner, you can also prove that B star star is equal to B and C star star is equal to C. I have not done the algebra here. This is just a homework for you. You can try it. Actually, when you will define this B star star, how we will define it? You know, this is defined as C star cross A star and divided by A star dot B star cross C star. Okay, B star cross C star. And now we will take actually the scalar product of this with B star dot B. Okay. And in the similar manner, when you will proceed, you will get this result that B star star is equal to B, and in the same way you can also prove that C star star is equal to C. So from here you can see easily that at the place of A star in this equation 1, now we can write A. Okay, and so A will be equal to B star cross C star divided by A star dot B star cross C star. And similarly, B is equal to this much and C is equal to this much. So from these results, it is obvious that the reciprocal of the reciprocal lattice is the direct lattice. Okay. So in this way we can prove it. I hope you have understand the calculation. Okay. Now the second very important property, you can see it here. This property says that the volume of the unit cell of a reciprocal lattice is inversely proportional to the volume of the unit cell of direct lattice. It means in this property we have to prove the volume of the direct lattice is just the inverse of the volume of the reciprocal lattice. So if you consider that this V is the volume of direct lattice and V star is the volume of the reciprocal lattice, then according to this property we have to show that this V star is inversely proportional to V, or V star will be equal to some constant divided by V. Actually, usually this constant will be either 1 or this will be equal to 8 pi square. You will see later on. Okay. So what we have to prove here? We have to show that the volume of the unit cell of the reciprocal lattice is the inverse or the inversely proportional to the volume of the unit cell of the direct lattice. So I have considered here you can see V is the volume of the direct lattice and A, B, C are the primitive translation vector of the direct lattice, and then you know that the volume of unit cell will be given by this formula. This is A dot B cross C. Okay. And in the similar manner, if you consider that A star, B star and C star are the primitive translation vector of the reciprocal lattice, then the volume V star, which represents the volume of the unit cell of reciprocal lattice, what will be that? We can easily say that this will be A star dot B star cross C star. Okay. And as I have told you, we have to show that this V star is inversely proportional to V. And for proving this fact, let us evaluate the value of this V star. Or in other words, you can say our aim is to relate this V star to V, where V star is the volume of the unit cell of the reciprocal lattice. Okay. So in accordance with its definition, this V star, which is equal to A star dot B star cross C star. Now according to the definition of the reciprocal lattice, you can say that instead of this A star we can write this expression. Okay. This is B cross C over A dot B cross C. Okay. And this B star, you know, this is equal to C cross A over A dot B cross C. And this C star is equal to what? This is A cross B over A dot B cross C. Okay. Now you can see in all these three terms, in denominator there is a scalar which is A dot B cross C, which represents the volume of the unit cell of the direct lattice, and this is just a multiplicative factor. This is just a scalar. So you can take the product of all these three factors in denominator. Okay. And so you can write this result like that. This V star is equal to 1 over A dot B cross C whole cube. Okay. And the remaining factors you can see, this is B cross C dot C cross A cross B. Okay. So I have written it here. You can see this is B cross C dot C cross A cross B. Okay. Now this A dot B cross C, you know, this is volume of the unit cell of direct lattice, which I have assumed V. So you can write it as 1 over V cube. Okay. And B cross C is here, you can see. Now see this product C cross A cross B. This is actually the vector product of 4 vectors. Okay, vector product of 4 vectors. And I hope you have definitely studied in your vector algebra course the product of 2 vectors, product of 3 vectors and product of 4 vectors. So this is the vector product of 4 vectors, and according to the definition of vector product of 4 vectors, you can simplify this result. This C cross A cross B. This is written as, according to the definition of vector 4 product, this is C dot A cross B times A minus A dot A cross B times C. This is just the definition of the vector product of 4 vectors. Okay. But as you know that this A dot B, A dot A cross B, see the second term, this will be equal to 0. Why this is 0? Because you know, according to the definition of vector product of two vectors, if you consider that this A cross B is equal to D, then you will write it as A dot D. Okay. And you know, if D is equal to A cross B, according to the definition of vector product of two vectors, this D is perpendicular to both the vectors A and B. Okay. So D is orthogonal to A, and you know the scalar product of two orthogonal vectors is equal to 0 because it is equal to AD cos 90, and cos 90 is 0, so this result will be 0. So this second term vanishes, and so I have written it here. You can see that A dot A cross B is equal to 0. So we will omit the second term, and the remaining terms will be what? This V star will be now equal to 1 over V cube times B cross C dot C dot A cross B times A. Okay. And this can be written as C dot A cross B times B cross C dot A. But you know, the scalar product is commutative, so B cross C dot A, this can be written as A dot B cross C, because a scalar product of two vectors is commutative. So the second factor will be A dot B cross C. Okay. Now C dot A cross B, this is just equal to A dot B cross C. Okay. And so both of these factors are same, and you can write it as V star equal to V square over V cube, because you know A dot B cross C, this is the volume of the unit cell of the direct lattice. Okay. And so this is V square, and so V star is equal to 1 over V. So the property which I have mentioned, that the volume of the unit cell of the reciprocal lattice is inversely proportional to the volume of the direct lattice, you can see the property has been proved. Here at the place of constant there is 1. But you know, when we will use the definition A star equal to 2 pi times B cross C over A dot B cross C, and similarly you will use B star equal to 2 pi times C cross A over this V. I have written V instead of this, and C star equal to 2 pi times A cross B over V. Actually, when we will use this definition, then at the place of number 1, there will be 8 pi cube, because 2 pi times 2 pi times 2 pi, that will be 8 pi cube. Okay. So when we will use this prescription, then V star will be equal to 8 pi cube over V. Here V star, you know, this is volume of the unit cell of reciprocal lattice, and V is the volume of the unit cell of the direct lattice. So you can see that the volume of the unit cell of the reciprocal lattice is just inversely proportional to the volume of the unit cell of direct lattice. So this second property which I have mentioned is also proved here, and I hope you have clearly understand the calculations. Okay. Now see the third important property of reciprocal lattice. This property says every reciprocal lattice vector sigma HKL is normal to the lattice plane HKL. This is just the definition of the reciprocal lattice vector. It means if you consider there is a set of parallel planes defined by HKL, where HKL you know are the Miller indices, then this sigma HKL, which represents the reciprocal lattice vector, this reciprocal lattice vector is normal to the set of parallel planes defined by the Miller indices HKL. Now we will prove it. If your aim is to prove that this sigma HKL is perpendicular to the plane HKL, how we can proceed? In fact, whenever we have to show that there are two vectors which are perpendicular to one another, there is only one mathematical tool. You have to find the scalar product of those two vectors. And if the scalar product of two vectors is 0, definitely you can say that the two vectors are perpendicular to each other. So here we have to prove that the vector sigma HKL is perpendicular to the plane HKL. So we will consider some arbitrary vectors in the plane HKL, and we will find the scalar product of this sigma HKL with those arbitrary vectors lying in that plane. And if the product will be 0, then we can easily say that this sigma HKL will be perpendicular to any line lying in that plane, and in other words you can say that this sigma HKL will be perpendicular to that plane. And for proving this, you can see this figure. Here I have considered a plane HKL, this PQR, see the figure. This PQR is the HKL plane as I have considered. Okay, this, see the figure, PQR. This is HKL plane. And O is the arbitrary origin. Okay. Now, this plane has intercept A by H, along the A axis. This OP is the intercept of this plane along the A axis, and so OP will be equal to A by H. You can see. Okay. Now, along the B axis, the intercept of this plane is B by K, and this B by K is equal to OQ, as you can see. Okay, this is B over K. And along the C axis, the intercept of this plane is OR, and this OR then will be equal to C over L. Okay, C over L. Now we consider that this vector RQ is equal to A. This is an arbitrary vector. I have assumed it. And the vector QP, we assume that this is equal to B. This is B. Okay. Now, if we will be able to prove that this sigma HKL, that is the reciprocal lattice vector, is perpendicular to vector A, and it is also perpendicular to vector B, where A and B are lying in this HKL plane, then we can easily say that this sigma HKL is perpendicular to the plane HKL. Okay. And for this, let us try to find first of all from the geometry of figure this B and A. And you can see I have made the calculation here. All those things I have mentioned it here. You can see PQR be the plane represented by HKL, but closest to the origin O. OP, OQ and OR are the intercept of the plane on the axis A, B and C respectively. So OP is A by H, OQ is B by K and OR is C by L. Okay. And arbitrarily we have considered RQ is equal to vector A and QP is equal to B. Now from the geometry of figure you can see that this OQ vector plus QP vector will be equal to OP vector in accordance with the triangle law of addition. So I have written it here, OQ plus QP is equal to OP, and so QP will be equal to OP minus OQ. But you have assumed that this QP is equal to B, and OQ you can see this is equal to B over K, and OP is A over H. So vector B is equal to A over H minus B over K. Now we will take the scalar product of this vector B with sigma HKL. But before that, how this sigma HKL is defined, you have learned in the previous lecture, in the first lecture on reciprocal lattice, that if A star, B star and C star be the primitive translation vector of the reciprocal lattice, then sigma HKL is defined by this. You have learned in the previous lecture. This is HA star plus KB star plus LC star. Now let us take the scalar product of B with this sigma HKL. Why we are taking a scalar product, I have just mentioned earlier that our aim is to show that this sigma HKL will be perpendicular to any arbitrary vector lying in the HKL plane, and B is an arbitrary vector lying in that very plane. So I have taken here the scalar product of B with this sigma HKL. Okay. Now you know this B you have obtained just this is A over H minus B by K. Okay, and dot sigma HKL, and sigma HKL is this much. Now take the scalar product separately by the two vectors. So this can be written as A over H dot HA star plus KB star plus LC star, and minus B over K dot HA star plus KB star plus LC star. Okay. Now take the scalar product of this HA star plus KB star plus LC star with A by H. So in the first term, what will be your result? This will be H over H times A dot A star. Okay, A dot A star. And you have learnt that A dot A star is equal to 1. Okay, you can also write it 2 pi, but here I am considering the prescription 1. So this is simply 1 because H over H will cancel out. Okay, and now we will take A by H dot KB star. So here there will be K by H times A dot B star. But you know, you have learnt in the first lecture that A dot B star is equal to 0. So at the place of that, I have written here 0, you can see. Then we will take the scalar product of A by H with this LC star. So this will be what? This will be L by H A dot C star. But again you know that this A dot C star is 0. So this term is also 0. I have written it here. Okay. Similarly, in the second term, you know, only B dot B star will be equal to 1, and B dot A star, B dot C star will be 0. So the first term will be 0, third term will be 0, and only the second term will non-zero, and that will be K over K times B dot B star, which is 1. So this is K by K, and that will be 1. So what is your result? You can see this is simply 1 and this is simply 1. So this is 1 minus 1, that is 0. So finally we get that the scalar product of this arbitrary vector B with the reciprocal lattice vector sigma HKL is equal to 0. Okay. Now see the figure again. I have considered that this RQ represents another arbitrary vector, and that vector I have considered A. Now we will also take the scalar product of this A with the sigma HKL. And for this, first of all, again apply the triangle of addition. You can see this OR plus RQ, that will be equal to OQ. Okay, and so this RQ will be equal to OQ minus OR. RQ will be equal to OQ minus OR, and therefore you can say that this A will be equal to B over K minus C over L. Okay, and it's a scalar product with this sigma HKL. Here there will be L. Okay, sigma HKL. You have obtained that A is equal to B over K minus C over L, and sigma HKL, this is HA star plus KB star plus LC star. Now again take the scalar product. You know, when we will take the scalar product with this B by K, the first term will be 0, because in the first term there will be a product of B dot A star, and that will be equal to 0. So I have written here 0. In the second term, there is B star, so there will be B dot B star, and you know this is equal to 1. So the second term is K over K. And again the third term will be 0, because B dot C star will be equal to 0. And then we will take the scalar product with minus C by L. So here is minus sign, and C dot A star is 0, so first term is 0. C dot B star is 0, so second term is 0. And in third term there will be C dot C star, which is 1. So this is L over L. And again the result is 1 minus 1 equal to 0. So what we get? You can see that our result is A dot sigma HKL is equal to 0. Okay, and therefore you can say that A is perpendicular to sigma HKL. Okay, so in this way we have considered actually two arbitrary vectors A and B in HKL plane, and we have taken the scalar product of those arbitrary vectors lying in HKL plane with the reciprocal lattice vector sigma HKL, and our result is 0. So we can easily say that this sigma HKL will be perpendicular to any line drawn in that plane, and therefore we can easily say that this sigma HKL is perpendicular or normal to the plane PQR, that is the plane HKL. Okay, so remember this property. This is just the definition of the reciprocal lattice vector, that if sigma HKL is your reciprocal lattice vector, it means it will be definitely normal to the set of parallel planes defined by the Miller indices HKL. Okay. Now the fourth property we are going to see is the spacing DHKL of the plane crystal lattice is equal to 1 over modulus of sigma HKL. It means if you are considering the parallel planes, these are the parallel planes, and suppose these planes are HKL plane, then the distance between two parallel planes is DHKL. This is also called interplanar spacing. And in this property it has been said that this DHKL is just equal to 1 over modulus of sigma HKL. Modulus of sigma HKL. It means the interplanar separation is just equal to the inverse or reciprocal of the magnitude of the reciprocal lattice vector. Okay. And for explaining this fact, let us again see this figure. I have considered here that this line represents the DHKL. That is, this is the interplanar separation of the parallel planes defined by the Miller indices HKL. And we consider that this n hat is a unit vector along this normal direction, along this direction. Okay. Now, you know that vector sigma HKL is along this normal. Okay. And if you want to write the sigma HKL vector in terms of the unit vector, then we can express it like this. This is modulus of sigma HKL times n hat. This is just a common technique. And you know, this sigma HKL is defined like this. This is HA star plus KB star plus LC star. And that's why n hat will be equal to HA star plus KB star plus LC star divided by modulus of sigma HKL. Okay. This is the unit vector along the reciprocal lattice vector. Okay. Now see this figure. Actually, when I have discussed in my earlier lecture the interplanar separation, then you have seen that if this normal makes an angle phi with a axis, then the interplanar separation DHKL can be expressed in terms of this angle phi. And actually that will be equal to what? You can see I have discussed it in interplanar separation lecture. So in fact, in that condition, this DHKL is equal to A over H cos phi. Actually, what is this DHKL? This DHKL is nothing. This is simply the projection of this vector A by H along this normal direction. So if this angle is phi, then projection of A over H along this direction, which is DHKL, that will be actually equal to A by H times cos phi. Okay. This projection of A by H along the normal direction is the interplanar separation. So you can write that DHKL is equal to A over H times cos phi. Okay. But as angle between this unit vector which is along this normal direction and A by H vector is phi, so this expression A over H times cos phi can be written as A over H dot n hat. This can be written like this. But n hat we have obtained is equal to this much, which I have defined in this equation 1. So at the place of n hat, now you can use HA star plus KB star plus LC star over modulus of sigma HKL. Okay. And so DHKL is what? This is A over H dot HA star plus KB star plus LC star over modulus of sigma HKL. Okay. Now take the scalar product. You can see when you will take the scalar product of A by H with the first term, there will be H over H times A dot A star. And you know A dot A star is equal to 1. So this will be simply 1. But when you will take the scalar product of A by H with the second term, that is KB star and LC star, that will be simply 0. Because you know A dot B star, A dot C star, all are 0. Okay. So only one remains in the numerator except this, yes, only one. And therefore, you can say that DHKL is equal to 1 over modulus of sigma HKL. So I hope you have clearly understand this property that the interplanar separation of the planes HKL, which is denoted by DHKL, that is simply equal to reciprocal of the magnitude of the reciprocal lattice vector. So these were the important properties of reciprocal lattice vector. Okay. Now in the next coming lecture we will see some more important property, particularly we will show uh, what will be the reciprocal lattice of a BCC lattice, what will be the reciprocal lattice to an FCC lattice, what will be the reciprocal lattice of a simple cubic lattice. All these things we will see in our next lecture. Okay, so I hope you have definitely enjoyed this lecture. So watch the video seriously, write down all these things in your notebook, and definitely then you will get most benefited. Thank you very much.